input the response due to the inputs, which is zero state response. We got it as what it was, minus half e raised to minus 2t, then plus 2 e raised to minus 3t, minus 3 by 2 e raised to minus 4t. So this is what we found out. So these two, if you are asking about it, that is basically the effect of the natural response. So this is a natural response. Okay, so this is the forced response. But natural response, this is not complete. That's what I was telling. There is also a natural response due to the non-zero initial states, so which is not present here. This is assuming zero state. ZS means zero state. If the system is at zero state, then when you excite it with a particular input, then it will have a response which contain two parts. One is the natural response and the other is the forced response. So for a system which is at zero initial conditions, if you do with the normal differential equation method, then you will get this as the natural response and this as the forced response. So this is the particular integral and this is the complementary solution, provided the system has zero initial conditions. But if the system also has non-zero initial condition, there is an additional part which is not mentioned here. So the other method, what we usually do is we find out the complementary solution and we don't write the constants here. So that constants will be unknown, and that will be so complementary solution, or yc of t, we will write it as a into e raised to minus 2t plus b into e raised to minus 3t. Then we find out the particular integral, okay, the particular solution yp of t, and that we will get it as minus 3 by 2 e raised to minus 4t. So this way you will get two result, okay, and then you will say the total solution is the sum of these two. So I am just outlining what you would do in a mathematical method of solution, so which is basically sum of this and this. Okay, so so that is y, that is your y of t, which is the total. Okay, total is this. So the total solution is basically a e raised to minus 2t plus b e raised to minus 3t, then minus 3 by 2 e raised to minus 4t. So this is the total solution, but we still don't know what is a and what is b. So there comes the initial conditions. Okay, you need to apply the initial conditions. This solution is valid for what? T greater than or equal to 0. So the initial condition that we would require here in this particular case, we need to know. So if we know y of 0 plus and y dash of 0 plus, then you will get two equations from which we can find out these a and b coefficients. If we know y of 0 plus and y dash of 0 plus, then a and b can be found out. Okay, so this is the approach. This is the outlined method for mathematical method. This is what you usually do it in mathematics, but there the initial condition requirement is 0 plus, okay, because this solution is valid for t greater than or equal to 0. So if what is given in the question is 0 minus, then from 0 minus you need to find out 0 plus. Okay, so which if it is a circuit, then the job is quite easy, because you know how the capacitor voltage is in the circuit. It cannot change abruptly. Okay, if you apply a finite input, it cannot change abruptly. Only exception is if you apply impulse input. Okay, in that case it is a different special case, but otherwise if the input that you apply at time t equal to 0, if it is a finite value, then capacitor voltage cannot change abruptly and inductor current cannot change abruptly. So from that you can figure out what is y of 0 plus and y dash of 0 plus given y of 0 minus and y dash of 0 minus. So that is the approach, the other approach.
Yes, sir.
Okay. All right. So let's now look at one more thing, that is what is the Laplace transform. Laplace transform of, okay, unilateral, let's say unilateral Laplace transform of integral minus infinity to t f of t dt. So we have found out the Laplace transform of d by dt of f of t given f of t Laplace transform. Okay, so the question is like, given f of t has a Laplace transform f of s, then find the unilateral Laplace transform of this. So that is the question. So how do we do this? Okay, so this is a very important problem. So how can we do this? Okay, so what we can do it is, like, since we are interested in unilateral Laplace transform, this integration we can split it into two. Okay, so the given integral, that is from minus infinity to t f of t dt, you can split it into two parts. One is minus infinity to 0 minus f of t dt, because when you find the unilateral Laplace transform, you won't take into account of that part. You don't integrate it in the expression for Laplace transform. Okay, you start integrating from 0 minus only, and then you have 0 minus to t f of t dt. So here I can take the integration variable to be a different thing. That may be a better idea, I feel. Okay, so let me just change the integration variable to be f of tau d tau. Okay, so everywhere let me change this. Just a variable. Okay, I can put t also, but just to not confuse with the t and tau, let us just separate. Okay, so that is it. Now when we say we are taking the Laplace transform, okay, Laplace transform unilateral of this, okay, again this one, I can now write it as Laplace transform of this first part plus the unilateral Laplace transform of the second part. It is from 0 minus to t. So I am assuming that t is greater than or equal to 0. Okay, t, if it is negative, then the second part will not make any sense. It will be 0. Okay, if t is greater than 0, only then you will have this two separation. Otherwise, only the first term will be there. So 0 minus to t f of tau d tau. Okay, is one thing. Now if you look at the first term, so what is the Laplace transform of this term? Okay, so when you integrate from minus infinity to 0, so Laplace transform of the first term, that is from minus infinity to 0 minus f of tau d tau. When you find this out, you have to apply the formula 0 minus to infinity, and then you put the function, which is the integral from minus infinity to 0 minus f of tau d tau, okay, into e raised to minus st dt. So this is our formula. Now what is it amounts to? So this if you look at after this integration with respect to tau, you will get a constant. You will get a constant, and you are basically taking the Laplace transform of that constant. Okay, because the t integration starts from 0 minus, which happens after this integration is completely over. So only thing is that whatever is this in this, so this can be treated, whatever is in this bracket can be treated as a constant, and you can take it outside, because there is no t here. So that is why I purposely changed the variable to avoid those confusion. And then it is like 0 minus to infinity e raised to minus t dt. Now this is basically the unit step function, right? Laplace transform of unit step function, which we know it is 1 by s. So therefore the answer to the first part is quite simple. You just perform this integration and then divide it by s. Okay, so this we have earlier found out that it is the Laplace transform of unit step function, and it is equal to 1 by s. So 1 by s, this is equal to 1 by s. So 1 by s multiplying with this factor that we taken out of the integral, which is a constant. So that is number 1. Now we need a Laplace transform of the second part, and then finally the total result is sum of these two. Now the second part, that is not a constant, because there is t there in the upper limit of the integral, there is t there, and we are integrating from 0 minus only, and our t integral in the Laplace transform definition is also for t greater than 0 minus. So the second part of the integral, let integral from 0 minus to t x, what was it, f of t, what did I do, f of t, yeah, f of. So the second part I am taking, and then I am saying this integral, it will be a function of time. Let's say it is equal to g of t. Okay, this integral from 0 minus to t, this integral I am calling it as g of t. Then what does that mean? D by dt of g of t is what? So that is going to be f of t. Okay, so if it should be more precisely if I say it is f of t minus f of 0 minus. So that is what we will get, and therefore Laplace transform of d by dt of g of t will be what? Is basically a Laplace transform. Okay, this will be this we already know. So if this is given, that is g of t has a Laplace transform g of s. What is g of t? I am calling this as g of t. Okay, and then if I have the Laplace transform g of t as g of s, then the Laplace transform of derivative of that function is what? So that we know. So that is basically s into g of s minus small g of 0 minus. So if okay, so there are two terms here which I split it into two terms. The g of 0 minus is basically the first term. Okay, so this is basically g of 0 minus. But for the moment, let us assume that that term is not there. Let's assume that so this is equal to s g of s if g of 0 minus is also 0, which is not really 0. Okay, but let's assume that if it is 0, let's see what happens. So if it is 0, then we have so this is derivative of this is equal to f of t. So Laplace transform of f of small f of t. Small f of t is equal to s into this, and so that we will call it as f of s. That is, f of s is equal to s into g of s. Now what we wanted to do is basically what is g of s. Therefore g of s is equal to f of s divided by s. So that is what finally we will get, provided g of 0 minus is 0, which is not really true. So there is a term coming from g of 0 minus, but we have already found out the Laplace transform of that term, which is basically given us that integral divided by s. So now what we can do is, like, we can find the total Laplace transform, which is basically sum of these two. Okay. So therefore Laplace transform of the total, that is from minus infinity, if I take minus infinity to t f of t, so okay, let's say tau and d tau is going to be equal to the term okay, the first term which we earlier found out, which was basically integral from minus infinity to 0 minus 0 minus f of tau d tau. Okay, this divided by s, that was the first term, which is corresponding to this, plus this result when this is 0, which is f of s divided by s. So this is the final result. So what I did, let me repeat what I did. So I wrote the integral into two parts, and the first part is basically independent of t, and therefore we can treat it as a constant in the formula for finding the Laplace transform. So I pulled it out, and the remaining integral is basically same as that of the Laplace transform of u of t, and which I know it is 1 by s. So this constant divided by whatever I pulled out divided by s is the first part. Then what I did was, like, assumed that the second part is 0. The first part is 0. Okay, this g is what? G is basically integral of 0 minus to t, that is g. So g of 0 minus is what? So g of 0 minus is basically integral from minus infinity to 0 minus, okay, of f of t, from according to this definition. Okay, so if this is g of t, just replace t with 0 minus, that will give you g of 0 minus. So I am assuming that g of 0 minus is 0, and under that assumption I am finding what is the Laplace transform of derivative of g of t. Because derivative of g of t, I know that it is s into g of s minus g of 0 minus, and g of 0 minus I am assuming it to be 0. okay, because whatever is its contribution I have already found out separately. So therefore I am assuming if it is 0, then what is a Laplace transform, which I am getting it as f of s by s. Now if it is not 0, I will have to add that term corresponding to that. Okay, so this is the way we this is one way. There is an alternate way of finding this out also. Okay, so now why did I discuss this? This is also sometimes required to solve problems. This result is also just like the differential result. We would require this also to solve problems. So let me try to take another problem, which is basically a practical circuit problem. So where we have both the integral as well as differentiation, both comes in, or in integral differential equation arises. Okay, so let's look at a problem.
Sir,
Yes.
sir, can you please briefly explain about all the steps once more?
Okay, so what I did is I splitted the integral into two parts. Okay, and I called this part as g of t. Okay, this part I called it as g of t, and this is basically g of 0 minus. Okay, this integral I call it as g of t. Here if you look at this integral, I call it as g of t. So if I put a t equal to 0 minus, so that will be g of 0 minus, right?
Yes, sir.
Yeah. G of, in the way I have defined g of t, actually this is from 0 minus to t. Okay, so there is nothing to integrate, so I should not put here, maybe that was a confusion. So this is 0 minus to 0 minus, so it should be 0. Okay, but this integral has the given integral has integration from minus infinity to t also, right? So here so this is what I am calling it as g of t. This is what I am calling it as g of t, and this is some integral. So first I found the Laplace transform of this first part, and then I found out Laplace transform of the second part. That's what I did. The Laplace transform of the first part is what? The Laplace transform of the first part is just you substitute this first part into the definition of the Laplace transform. 0 minus to infinity, you have this function which you multiply with e raised to minus st and integrate it, right?
Yes, sir.
So now if you look at this bracket, there is no function of t there. So it's a constant. You can pull it outside the integral. Agree?
Yes, sir.
Okay. So then if you look at the remaining part, it is basically it's basically u of t into, you can write like this, right? U of t e raised to minus st dt, which I know it is 1 by s.
Yes, sir.
Because u of t is 1 for positive values of time. So whether u of t is there or not, it doesn't make any difference. So if you put u of t, I can make it from minus infinity also. But whatever it be, we have solved this problem early on, and we got that result as well. So now we have another part which is from 0 minus to t, which I call it as g of t. Then what is the Laplace transform of derivative of g of t? According to the formula, it is basically s g of s minus g of 0 minus. But g of 0 minus, according to the definition, it is what? It is 0, because it is 0 minus to 0 minus integration, right?
Yes, sir.
So that means s into g of s is basically Laplace transform of f of t. Derivative of g of t is f of t.
Yes, sir.
So therefore f of s is s g of s, and g of s is f of s by s.
Yes, sir.
So that is
Yeah.
basically the second part. So I added the first part with the second part, right?
Yes, sir.
Okay.
Yes, sir.
Okay, so now let's try to do a problem which require this result. So the problem is basically a circuit is given. So this is maybe a problem that you will come across in your network theory, similar problem. So there is a 10 volt here, and there is a inductor here, and there is a resistance here, there is a switch here, and there is another resistance here, then there is a capacitor here. This is a problem I am taking from the book itself. Okay, and what happens to this switch at t equal to 0? This switch is getting open. Okay, initially it was closed, but t equal to 0 it gets open, and this is 5 ohm, and this is 2 ohm, and this is 1 by 5 farad. Okay, these are the values, and here it is 1 Henry. This is the circuit. Okay, now what is the question? The question is in this circuit the switch is in closed position long before t equal to 0. So for a long duration the switch was closed position. Okay, then long before t equal to 0, when at t equals 0 it is opened. It is opened instantaneously. Find the inductor current. Okay, y of t. Find the inductor current y of t for t greater than or equal to 0. So this is a question. Okay, so if you know the differential equation in initial condition, now you already learned how to solve it, but here differential equation is not given, it is a circuit that is given. So that is why it is a network theory problem. So read the question carefully, and you need to write the differential equation, you need to find the initial conditions also. Okay, so and the initial conditions at what time we require? Just before the switch is getting closed. That is what we require. Just before the switch is getting open, what was the situation? So what can you say about it? What is the initial condition? So whenever you see an inductor as well as a capacitor in a circuit, you should know that inductor current cannot change abruptly, because there is no infinite voltage applying anywhere. So inductor current cannot change abruptly, and capacitor voltage also cannot change abruptly. So if this switch is closed, so before t equal to 0 time, if you look at the switch is like or the circuit is like, so before t equal to 0, how does the circuit look like? The circuit look like this. There is no switch here. I am removing all the switch. There is a 10 volt battery, and there is a 5 ohm resistance, 2 ohm resistance, 1 Henry, and then 1 by 5 farad. So this is 10 volt. So, and it has been like this for a long time, which means all the transients have gone. That's the meaning of it. All the transients have gone, they have died out, and only you need to look at it as a steady state thing. So this, if it is remaining like this for a long time, you should be able to know that the inductor can be replaced with a short circuit. Probably you might have learned this in network theory. And the capacitor should be replaced with an open circuit. So there is 5 ohm, 2 ohm, 10 volt. So what is this voltage? The capacitor voltage. What is the capacitor voltage? It's very easy. You don't need to even to write a.
5 ohm. So voltage across 5 ohm.
Yeah, what is the capacitor voltage? You see the capacitor here, I have made it an open circuit. So there is a voltage on the capacitor. What should be that voltage? If the circuit is remaining like this for a long time, I said I can remove the inductor with a short circuit and capacitor with an open circuit. And what will be the voltage on the capacitor? And that is one question. And the second question is what is the current here, which is what is called as y of 0 minus. What is this current and what is this voltage? These things are the initial conditions. Capacitor voltage, inductor current. Quickly tell me. It's a simple circuit, right? So what is the problem? What is Vc of 0 minus and y of 0 minus? Current is called by y of t, so I am calling it as y of 0 minus. Quickly, do you know or not? I can't wait for long. Just say yes or no, otherwise you tell the answer.
Sir, can we apply network theorem, sir?
Can you tell the answer? It's
Yes,
a very simple. By inspection you can tell. You don't need to write any equation or anything like that. It's a very simple circuit. 2 resistor, 1 voltage source. So what is this current? Y of 0 minus? Or you want to say you don't know? Say it something, because we have to proceed.
Sir, 7 ampere.
7 ampere. How did you get 7 ampere?
Sir, 2 and 5 in parallel.
No. This is open.
Okay. So then 2 ampere.
2 ampere. 10 by 5.
Yes.
2 ampere.
Yes, sir.
Yeah. So this is equal to 2 ampere. And what is this capacitor voltage?
Sir, 10 volt.
10 volt.
Yes, sir.
Okay, very good. So we got the two things just before the switch was closed, or switch was opened rather. The switch was closed for a long time, and just before the switch was closed, the situation is that through the inductor we had a current flowing, and across the capacitor there was a voltage 10 volt stored. Okay, 10 volt is the voltage stored. Okay, so that is the case. So now again, now let me write after the switch is getting opened. I am redrawing the circuit. So 10 volt, 1 Henry, and then what was here? There is a resistance but now this switch is open already. So if this is open, then there is no point in drawing this part. So let me remove that part. There is a resistance here. It's just a series RLC circuit now. There's a capacitor here, but this resistance was how much? This resistance was 2 ohm, and this capacitor was 1/5 farad. There was a voltage here VC of 0 minus, which was 10 volt, and there was a current here which is Y of 0 minus, which was 2 ampere. So this is now our problem. So we just need to find out the expression for Y of t. This is the current flowing through the circuit, because once you open the middle part, there is no current flowing through it, so I removed that part. So far, are you with me? Is it clear so far?
Yes, sir.
Okay, so now what we can do is, let us write down the KVL, because it is a loop, right? Single KVL equation I can write. So what is the voltage in each of this? L d I by dt. L dy by dt. Y is the current, so instead of I we are using Y. Then plus 2 into Y of t, that is Ohm's law, plus 1 by the capacitor value, which is 1/5, 1 by c integral minus infinity to t y of tau d tau. So this is like integral I dt, 1 by c integral I dt, that is the capacitor voltage. Okay, capacitor voltage. This is the resistance voltage, and this is the inductor voltage. So add all of this, I should get how much? 10, and this is at a time we are looking, so this is t greater than 0, greater than or equal to 0. Okay, this is valid only for t greater than 0, so I can write 10 u of t. Okay, this is from t greater than 0, so I am putting u of t here.
Sir.
Yes.
Sir, I have one confusion, sir.
Sir,
as soon as we remove the 5 ohm resistor, won't that current be changing 2 ampere or a voltage across capacitor 10 volt?
That's what I'm saying. I'm coming into that. Okay, so this is the picture. The moment you have removed the switch, open the switch, and so once you open the switch, definitely no current can flow through that part. So we remove that part because it doesn't make any effect on the working of the circuit, the remaining part of the circuit. Okay, so now the thing is that two principles that you should the most important principle that you learn from the network theory class is that one is that inductor current cannot change abruptly. You cannot have that. Second is that capacitor voltage cannot change abruptly, provided there are no infinite valued voltage source. Provided there are no infinite valued voltage source. So that is the case in this particular. There is no infinite valued, like an impulse which has infinite magnitude at t equal to 0. Nothing like that is in this circuit. It is basically a step input. Okay, sudden, abrupt means it's like a step change. So this is a guiding principle that you have to know. Then only you will be able to find out the initial condition. We have almost found out the differential equation, but the next thing that you require is basically the initial conditions. Then only you can solve this problem. So that is clear.
Yes, sir.
Yeah. Okay. So this is the KVL that we have. Now what we have to do, we have to take the Laplace transform. So step 1 was this. So this is step 1. Write the differential equation. We had one additional step compared to our previous problem. We never had to, it was given to us. Okay. Now step 2, taking Laplace transform, unilateral Laplace transform on both sides. Okay, so now let's substitute the value of L. L was 1, right? L was 1. So this is 1. The inductor was 1 Henry. So when you take the Laplace transform, now tell me what is the first term? S y of s minus y of 0 minus. That's a property. Then next 2 into y of s plus. Now we have basically 5 into something. 5 into what? 5 into 2 terms. I can split it, minus infinity to t, 0 minus y of tau d tau plus integral 0 minus to t y of tau d tau. So this is basically we are just splitting it, or you can just substitute the formula also. Okay, so if you substitute the formula which I derived for integral, what was it? This divided by s, that was the first term, and the second term was what? Y of s by s. Clear?
Sir.
That was the result that we derived, and the reason why I derived it is so that you can do this type of problem. Okay, I applied the result that we derived here. Okay, the Laplace transform of this term is this. Okay, alright, so that is the LHS here. Now what is the RHS? RHS is simple, it is 10 by s. That's it. That's the input. There is no other term there. So all you now need to know is to solve this differential equation, what you need to know? You need to know this, but you know already that. You said it is 2 ampere, right? Isn't it? You said it is 2 ampere, I of 0 minus. You said it is 2 ampere. Okay. Yeah. Then so what we now require is basically what is this thing? What is this integral? Do you know that? We know the capacitor voltage, so we can find it out. What is the relationship? What is the relationship?
Sir, can you please repeat the question?
What is this highlighted portion? What is the value of this? Can you tell me? We know Vc of 0 minus, right? We know Vc of 0 minus. That is 10 volt, you said, right? Now what is
Yes,
Vc of 0 minus? It's basically 1 by c integral from minus infinity to 0 minus y of tau d tau. Okay, and that is 10 volt, which means what? Our required integral is minus infinity to 0 minus y of tau d tau. What is it? It will be 10 volt into C,
C. Yes, sir.
which is 1 by 5. that is 10 by 5, which is 2, right?
Yes, sir.
Yeah. So C is given as 1 by 5. I just multiply it with the capacitor voltage, okay, and that way I got this part. So now we got everything. Problem is almost solved. So only now we need to rearrange the terms. So therefore S, here S is there, here 2 is there, then here 5 by S is there, into y of S. Then what else? This is minus 2, so this is minus 2, and here we have 5 into this one, which is 2, so that is again 10 minus or plus 10 by S. Is that clear? 5 into whatever is this, which is 2, 5 into 2, that is 10, 10 by S, and this term I already taken. All the term on the left hand side is done, and that is 10 by S. So these two terms are initial conditions. Okay. These two terms, or I can say these are due to initial conditions, and this is the input applied. So if I want them separately, I have to segregate them and keep them separate. So therefore S plus 2 plus 5. Okay, let me just simplify this also. Let us simplify this also. Take the LCM, S, that is S square plus 2S plus 5 divided by S, divided by S into y of S is equal to, here also let me take the LCM. So 2S minus 10, I am taking to the other side, so it is minus 2S plus 10. It will become, when I take it to the other side, it will be 2S minus 10 by S. So that is the initial condition part, and then I have 10 by S, which is the input applied. Okay, so S everywhere, which is a good thing. We can cancel all these S. So therefore y of S is 2S minus 10 divided by S square plus 2S plus 5, that is one term, plus 10 by S square plus 2S plus 5. Now if you don't want them separately, okay, if you only want the total response, you can see that there is a perfect cancellation that is coming, and it will be just equal to 2S by S square plus 2S plus 4. So it depends whether you want a zero state response or zero input response, or you just want the total response. So let me write it again. So y of t, that is y total, let me just write it as y of t, is basically y0 input response plus y of 0 state response is a Laplace inverse of what were the terms? 0 input response was I think 2S minus 10, 2S minus 10 S square plus 2S plus 5. So 2S minus 10 divided by S square plus 2S plus 5. Then plus we have a Laplace inverse of 10 by s square plus 2s plus 5. Okay, so if you require these two separately, then you need to categorize it like this, and so this one is this one, and this one is this one. But you are not interested in separating it out. I just want the total. Our question was just find the total response, so we don't need to categorize it. So I can also just write it as 2s by s square plus 2s plus 5, because this minus 10 divided by this and plus 10 divided by this, they will just cancel off. So that's what we need to find out. Now you see the roots are how? What are the roots? If I find the roots of s square plus 2s plus 5 equal to 0, or what? S is equal to minus b plus or minus square root of b square minus 4ac, that is 4 into 5, 4 by 20 by 2. These are the roots, right? There are two roots, and you see that square root of 4 minus 20 is not real. It's going to be complex. So this is minus 1 plus or minus square root of minus 16, which is j 4 by 2, that is 2. So these are complex conjugate roots. So therefore we need more work to do. We have more works to do. Okay. So 2s divided by s square plus 2s plus 5 is equal to, how we can write? A by s plus 1. If I take the minus here, then it will be plus j2. I can write like this. Okay, I can proceed like this: s plus 1 minus j2. This is one way to proceed. Okay, and then you can apply find a and b, and then alternatively, or let me show you that also. This is what I prefer to do in such cases. Alternatively, what I can do is, like, I write this as the product of these two terms. If I take, I will get basically x plus 1 square plus 4, or I can say 2 square. So this way I can write, okay, divide by 2s. Then what I would like to do is, basically, I try to bring this since there is s plus 1 here, I try to bring s plus 1 here. So I will write s plus 1 then minus 1 divided by s plus 1 the whole square plus 2 square, which is what? So the first term, if I take, that is 2 into s plus 1 divided by s plus 1 the whole square plus 2 square, and the remaining term, which is basically there is a 2 here and there is a minus 1 here, so it is minus 2, or let's keep the 2 at the numerator itself, because this term is 2. So it is 2 divided by s plus 1 square plus, so this is a standard term actually. So what I did is, I just manipulated it so that I will so therefore I will prepare it in standard format. So this is 2 into Laplace transform inverse of s plus 1 by s plus 1 the whole square plus 2 square then minus Laplace transform inverse of 2 by s plus 1 the whole square plus 2 square. So now you can write down. So this is what this is: e raised to minus t cos 2t. That's what this one is, into u of t. And similarly this one is e raised to minus t. I hope you are aware of this from my earlier class, sine 2t u of t. That's it. So I can pull out the common terms. E raised to minus t is a common term, then 2 cos 2t, then minus sine 2t, then u of t. So if you want, you can just leave it there, but you can also try to simplify it further. So if you want to simplify it further, what you see is the coefficient of this is 2 and here it is minus 1. So if you divide it by square root of 2 square plus 1, that is square root of 5, and so here also you can do that, and then here you have to multiply with 5, and then what you can do is like you can write this slightly neatly, or this is square root of 5 e raised to minus t, and this one I will write this factor. Okay, so this is cos 2t into what, into say cos 5, then minus then sine 2t into sine 5. This way I can do it. So that is equal to square root of t e raised to minus t. So then I can have the entire bracket as cos 2t cos can anybody tell me what is it? Cos a cos b minus sin a sin b, that is
cos a minus
cos a plus b, right?
cos a plus b, yes.
Yeah, cos a plus b u of t. So this is bit neat. Okay, so now you can see that there is going to be oscillations and they are dying out because of this term. Now what is phi? So to phi, okay, so let's find out phi also. So if I say tan phi, where tan phi is basically sin phi by cos phi. Sin phi is what? 1 by root 5, and cos phi is what? Cos phi was 2 by root 5. So there is a good cancellation here, so it is 1 by 2. So phi is tan inverse 1 by 2. Okay, but tan inverse 1 by 2 you have to just find out it from the calculator, and if you do that, since it is available in the book, I will just write it as 26. So therefore this is root 5 e raised to minus t cos 2t plus 26.6 degree. So that's it. Now if you plot this, you can see what is happening with the current through the inductor as time goes on. You remember what you told me, that the current is 2 ampere before time t equal to 0?
Yes, sir.
And now what is going to happen is that so you have to just find out some few values So there is a e raised to minus t here, which is a decaying function like this, but then it is multiplied with a cosine function, not exactly the cosine function, but a shifted version of cosine function, and the cosine function is shifted to the left, so you can write it as cos, I can take the 2 outside and write it as t plus 26 by 2, that is 13.3 degree. So little bit shifted to the right. So cos has a maxima here like this. You shift it little bit, the maxima will be shifted like this to this side. So that will be multiplied with the exponentially decaying function. So the overall effect, so this is the cos function, maybe I should. So the cos, which is shifted by 13 degree to the left. So this is the cos function which I have. I'm just drawing the cos function separately. But our function is basically product of these two, and then the whole thing is multiplied with the root 5. Okay, cos function will not come up to 2. Okay, that's a mistake. It will only come up to, or maybe I will say it is. Okay, let's leave that. To make it more accurate, if I want to write cos function, maybe I will write these two functions together, that is root 5 into cos function. So then it can go beyond, it will not just stop here, it will go beyond this. So it will go slightly beyond. Okay, square root of 5 is, I think, little more than 2. 2 point something, I don't know exactly, but let's say it is something like this. So the peak is somewhere here.
2.23, sir.
2.23. Okay, so if this is 2.23 maybe, so this is 1, 2, 3, maybe slightly above. Okay, not much above. Okay, so we are just doing an approximate plot. If you want accurately, you need to use a calculator, and so similarly this is minus 1 and this is minus 2. So here also it will go little larger than that level, and then it comes back. It keeps on oscillating like this. So that is the root 5 into cos function shifted by 13.3 degree. So how do I know shifting? I have to take the 2 outside, then only I can tell this. Now if I multiply this, okay, so one curve is this, or maybe I should not, okay, this daughter curve is exponentially decaying function, and that is multiplied with this cosine function. So the overall effect is going to be what? The overall effect is, in the left side it doesn't affect, cos doesn't affect, because it is only valid for, with a u of t is here, so it is only valid. So when you multiply these two, what is going to happen is it is going to reduce, maybe smoothly. Okay, it will be reducing smoothly, then it will go down, and then when the cos function becomes 0, this should become 0, because anything multiplied with 0 should be 0. And then you see that this e raised to minus t became very negligible here, so it will not rise much, and something like that. It may oscillate or may not oscillate further. That depends on exact values. But this is our y of t. This is our y of t. So that is how the inductor current changes. That means initially from 2 ampere in this circuit, the current will reduce. Current will reduce here. Okay, and then after some time the capacitor will get charged more, that is above 10 volt, which we did not find out. If that is also asked, you need to find out the capacitor voltage also. And then the capacitor will begin to discharge in the opposite direction. That is when the current direction is reversing. Okay. So this oscillation is because the resistance value here is relatively less. So that is why you are getting complex conjugate roots and these oscillations. If you don't get complex conjugate roots, you will not get oscillations, which is like our previous problem. So then what you will have is like if it was a higher resistance value instead of 2 ohms, then what will you get? You will get something like this. You will get something like, it will just go like this. Okay, something of that sort. This is called overdamped. Okay, so this is overdamped, but our results are showing underdamped response. It's a decaying oscillation. So let me just state that explicitly. What we have here is, so this result is underdamped. So second order system depends on the component values you will have. So you can try solving it for a larger values of resistance, and you will see that you will get real roots if you do so. So which component? I think this 2s is what you have to make it bigger. Maybe if you make it 10s or 20s, definitely you will see that the roots are going to be b square minus 4ac 20 if you take it will be just repeated roots. Okay, so that's it. I will close here.